Okay, welcome everybody. Morning. For today's lecture in cognitive psychology, and today we will have the second part on language. Okay, let's start with some theories on speech recognition, how to recognize speech. And you may know that I think the first one who really introduced that was Apple a few years ago, that you actually nowadays can talk to your mobile phone and ask about the weather or things like that. Did I turn the camera on? I'm not quite sure. Yes, I did. Okay, and this was not possible really until quite a few years ago, simply because the recognition of speech is a very complex process. And some of you may object and say, well, but for some time already you can dictate stuff to your computer. There has been software where you can type emails just by speaking into the computer. However, that usually is just the mere recognition of the words without any understanding of the meaning of the words. So you could have included some simple commands like type and make it boldface or something like that, but not in the way it works. It starts to work nowadays that you actually kind of can speak to your phone and can say something like, please make an appointment tomorrow at 4 p.m. with my GP or something like that, and it will be implemented in the phone. That's really new, and one reason for that is that speech recognition is quite a complex process. So let's have a look how humans do that. So first, in the human system, or the reasons why it is so complex, is that we have quite an interaction between syntax, that means the grammatical structure of a sentence, and semantics, that means the meaning of the sentence. We have seen last week that the meaning of a particular or of the identical word can be different depending on where exactly it is located in the sentence. So there is an interaction which makes it more difficult. You can't do it like straightforward, that word has that meaning, or as we will see today, the syntax will always be the same. The syntax may also be influenced by the meaning of the words, actually. Then we have seen that when we want to reconstruct the speech signal, that we have quite a bit of top-down influences, which have been illustrated by the phonemic restoration effect. To give you a brief reminder, that is when you listen to something and one phoneme is overlaid or covered by a cough or something so that you don't hear that. And you actually hear the phoneme which fits into the context, into the word. So there must be some information from semantics from top down here. And we have seen that the perception of language, of speech, is not only an auditory process. Of course, auditory information is sufficient, but that by demonstration of the McGurk effect, where we have seen, you see a face saying, I hope I remembered right, saying gaga, and you hear the baba, and then you actually perceive dada. So it's a multimodal process, and visual information actually influences our perception. So that all makes it a pretty complex process. And there are quite a few theories which have been proposed, because it is obviously a very central topic in human psychology or cognitive psychology or linguistics to understand how do we do speech recognition. And we will focus on three theories to give a nice overview of the different approaches, or an introduction to the different approaches. One is the motor theory proposed by Lieberman, Second one is the cohort theory, and finally this trace model, which is actually a computer model. And we'll discuss them in some more detail now. Okay, let's start with the motor theory of speech perception. It has been proposed by Alvin Lieberman in the late 1960s, so it's a rather old theory. And the theory is, at least at that time, very kind of counterintuitive or new idea. And the basic idea is that we understand speech the way that when we hear something, what we actually do is we use our motor system to actually internally mimic or reproduce what we heard. And by the activity in our motor system, we then do understand what has been said. So when I hear a word, let's say tree, then this acoustic signal activates my motor system so that my motor cortex is activated in a way as if I would produce the word tree. It's a bit like mental imagination. You try to imagine saying the word in your mind. And by this motor activity then the understanding comes into being. Nowadays there are quite a few theories and suggestions in different domains that this is maybe quite a more general phenomenon where we have the idea, okay, how do action and perception interact so closely, and how can that be? So that nowadays this is a very common idea of a common coding of action and perception. So the bottom line is the motor system is actually involved in both, in the production of speech as well as the perception of speech. There is a bit of support for this theory. One is the McGurk effect. And what here actually happens in the interpretation of the motor theory is that the visual information is interpreted as information about how the sound is produced. When we see the movements of the mouth and the lips, that's information that's motor information, so to say. So this information and not the sound itself affect perception. Then we have a phenomenon which is called categorical perception in phonemes, and that can be nicely explained by motor theory. What does categorical perception mean? That means we have phonemes, as we spoke last week. For instance, da and ta. And they can be defined, as we've seen last week, by the place and manner of their articulation. And we have seen we can create spectrograms of that, so that we even can produce them artificially by a computer program. Now, what we can do using a software, when we have these two extreme points, one is da, one is ta, we can create smooth transitions between them. I'm sure you have seen these morphing of phases where one phase morphs into another phase. The same we can do in the acoustical domain. The interesting thing is now what happens to our perception of the phoneme. And it has been shown that the perception is categorical. We can morph and smooth, and we always hear da, 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 until there's a certain point where it suddenly switches over to ta, 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 ta. So we don't have any perception of any smooth gradient between the two things when we morph that, but we really, our brain or our cognitive system categorizes this. It's either a da, and then we perceive it as a da, or it's a ta. Now, motor theory would explain that by the fact that we try to understand the phoneme by producing it. And we can produce only da or ta. We cannot produce any smooth transitions between that with our speech system. We can't do that. Only the computer can do that. So our motor system tries to get the closest match. As long as it thinks the auditory input matches to a da, it produces and mimics the da, so we understand it as da. And at some point it will think, okay, that was a ta. So it produces and mimics the ta. Further support comes from cognitive neuroscience. So for instance, when you do a brain imaging study where people have to listen to speech, you see that cortical motor areas, in particular premotor areas, are activated by that, just by the mere perception of speech. In addition, if you remember, we spoke about TMS, transcranial magnetic stimulation, where you can apply magnetic pulses to specific brain areas, and these pulses have like two effects. They result kind of in a synchronized discharge of all neurons below the magnetic coil. If you do it over the motor cortex, you will have a twitch of your finger, for instance. However, if you do it repeatedly, you kind of block the activity in that area. So what you actually do is you simulate kind of a lesion, or you inactivate, because all neurons have discharged. It takes a while until they can work normally again. So when you do TMS over the premotor cortex, the perception of speech is impaired in people. So from cognitive neuroscience, we have two lines of evidence here which point to the fact that actually motor areas in the brain seem to be really functionally involved in the perception of speech. There is a close link to, I'm sure you have heard of the concept of mirror neurons, which have been, so mainly the group around Rizzolatti, which have been observed initially in the premotor cortex of monkeys. And these mirror neurons fire when monkeys act, as well as if the monkey sees another person doing exactly the same actions. So as an example, here, I'm sorry that it's so low on the screen, you have activity of a neuron, and when the monkey actually grasps something, you have higher activity. And then the same monkey just observes another person doing the same movement, and the same neuron activates that, is activated as well. It should be noted that only some neurons in the premotor cortex are mirror neurons. So it's not like all neurons in the premotor cortex show that behavior. It's only some of them. And in addition, there is, although, I mean, I would say especially in the everyday media, this concept is a bit too stretched. So nowadays, every time when it comes about understanding something, like emotions, empathy or something, it's always like, oh, mirror neurons are involved. You really have to check closely whether there is evidence for that. And there are actually people who say, well, it has been shown in monkeys, but the evidence, the actual evidence that mirror neurons exist in humans is still far from perfect. So there are, for instance, some studies who would argue that in the lateral premotor cortex, when you do the right experiments, you actually can't find evidence for mirror neurons in humans. So I don't want to make a firm conclusion here, just to make you a little bit aware that maybe in the media this concept may be a bit too stretched and just generalized to everything where it would make sense. However, in the monkey, these neurons are in the premotor cortex. So if they exist in the humans, then it's most likely that they will also be at least in the premotor cortex. And these are exactly the areas which are activated during speech perception as well. So there is some convergence here. Of course, as every theory, motor theory also has some problems, and some of them are quite serious. So first of all, speech production is highly variable. So for instance, we all have different accents, and we may speak one and the same word in different ways, even within a single speaker, just depending on the context, for instance. So when we hear something, how do we determine which way or which mode of production do we use? So how can we map that directly? So if you have one word which can be pronounced in two different ways and we hear something, so we have to map that somehow. So that is a bit of a tricky problem. Or if we hear something in an accent which is not familiar to us, then mapping these, although we understand that, mapping that to our own motor system can be a tricky thing. Another problem is in infants, because infants are already quite good, or there is a period in development where they are pretty good at the perception of speech, but not at the production. So according to that theory, they should be bad at perception as well, because they don't have the means to internally simulate the motor act, because they can't produce yet, but they already can perceive. So that's a problem. So basically, the learning of speech must be based on different mechanisms, which seems a little bit too complicated for some reasons. And we have clear influences of top-down effects, as we have seen in the phonemic restoration effect or something. However, the motor cortices do not store meaning, so it's a little bit tricky to have the interaction or the top-down influences of meaning implemented or related to activity in the motor cortices, because meaning is somewhere else, and there are no in the brain, and there are no direct links between these areas. Okay, so to summarize the motor theory of speech perception, it has been revised several times, as it is usual. So you propose an initial theory, you provide some evidence in favor of it, other researchers find the research interesting, do also studies, and well, they find then evidence which is in disagreement, so you revise and so forth. So, and due to this somewhat unclear evidence, it is still debated. It is still like an active theory, so it's not like, oh, that's old, nobody cares anymore, but it's still not clear whether it's really the full story or not. Okay, let's turn to the next theory, which is called Cohort Theory, and that's a little bit a different approach, and it focuses mainly on a different aspect here. And it has been proposed by William Marston Wilson in the 1980s. And the cohort theory explains when we hear a word, how can we map it into our lexicon. And the lexicon is our storage, our memory of words, which we do know. So, and something which was not clear at the time he proposed is that we start to process and start to try this mapping as soon as we hear the first phoneme, and not only after we heard the whole word. Because it could easily be that we first have to perceive the whole word, and then we try to map it to some entry in the lexicon. And the initial observation for that theory was that in shadowing experiments, people actually, so shadowing is you hear something over headphones and you have to repeat that overtly and speak that out while you hear it. And in shadowing, it has been shown that people start speaking out the words although the words haven't been finished presenting. So there must be already some representation of the words, although the word hasn't been finished in presentation. Okay, so let's go through an example how cohort theory would explain the recognition of a word, and let's take the word candle as an example. So when we hear first ka of candle, that activates all words starting with ka, so the initial cohort. So for instance, that might be candle, the target word it will finally be, but also candy, can, cattle, and many other words which are called the competitors. Then we get the next auditory input, the N. So now we have can, and all the words which don't match anymore, or the mismatches like cattle, are then removed from our cohort, and it becomes smaller. So it's only candle, candy, can in this example, and cattle is removed. Now then the D comes, so we can remove the word can, and it becomes smaller and smaller, our cohort, until we have the so-called recognition point. That means that point where only one word is left in the cohort, so where there is no alternatives left. And after the recognition, when we have that, the word is selected from the lexicon and integrated into the context. So for instance, the sentence, to make meaning of the whole sentence. based on some evidence which came later, the cohort theory has been adjusted and adapted so that it states that in different stages of the processing we have different types of influences or different modes of processing. And rather early in the processing, when our cohort is still, our initial cohort is still big, we mainly have bottom-up processes. That means just phonemes are coming in and we reduce our cohort, that's all. However, later in the process, we also may have top-down influences in addition to the bottom-up processes. So for instance, the meaning of the surrounding sentence, the context, what we heard already, may provide us here clues of what the final target word actually might be. Okay, so let's switch to the trace model, which is a computerized model which has some similarities with the idea of the cohort theory. It was proposed by James McClelland, so a few years after the cohort theory has been proposed. And James McClelland is generally a guy who's doing a lot of simulation and computer simulations and things like that. So it's a so-called connectionist model. So we spoke about this in the beginning, and we will see an example actually in a moment. And as I said, it shares some similarities with cohort theory. So for instance, that there is a time course of word selection, and because it's a computer model, they can really calculate activation values of different words. And here's an example. So here on the y-axis you have the activity of the different words, and here you have time, and you see in the beginning all words starting with B, for instance, are activated, and then Bill, which differs, so bald is the final target word, and Bill, so first phoneme is, or second phoneme is different, then goes down in activity, and ball, which has the highest similarity, is selected or disregarded as a latest, so reaches the highest level of activity here. Okay, so this is a typical time course of how such a selection may occur. And by going through this example, don't think about too much in the context of like word recognition. You can use this example also to gain a more general understanding of how such types of models are actually working. So, because we go through that in a bit more detail in a moment. So that's the model as suggested by McClelland. And the idea is that on the one hand the processing is kind of bottom-up. So you start with basic auditory features, then you get to phonemes, and finally you get to whole words. And within each category or layer, you may say, you have different perceptual units, you may say, and they inhibit each other. You'll see that in a moment. That's called lateral inhibition. And the reason is that we want to have only one single output here. We want to have only one word selected. So it's the winner takes all. The word which is actually selected inhibits all other words as well, so that you get a very clear difference in activation level. Same happens for phonemes. However, you have context effects implemented by reciprocal or bidirectional activation and inhibition. So phonemes can activate words, but if words have some activation, they can activate their phonemes as well. Okay, so the auditory features, the most basic level, are basically reflected by the place and manner of articulation, and in the model it's actually implemented by a simplified spectrogram. Like we've seen last time, you have time and you have frequency, and they just represent different phonemes by these simplified spectrograms so that the model can work with that they don't need to implement a proper speech recognition machinery, which wasn't possible in the 1980s. Then we go up one level to the phonemes, and here the idea is that for each phoneme of a word, you have a complete set of potential phonemes in the serial position. So the first phoneme can be an A, and B, a C, and so forth until T. The second phoneme of a word can be again an A, a B, a C. So you have a complete set here. And the lateral inhibition, what we spoke about, is about the phonemes for position 1, so that we get one winner. The first phoneme may be identified as C. So all other phonemes are inhibited by lateral inhibition. It doesn't mean that the phonemes of the second position are inhibited. That's a different thing. Second phoneme may be an A, so all other from B to Z are inhibited. And this then results in this winner-takes-all principle, so that we only have one phoneme for each serial position. And finally, we go to the level of words, which basically reflects the lexicon of the speaker, or in this case of the model. And in trace, in this model, this is limited to one-syllable words, so the very short words only. And again, we have this lateral inhibition, which is often shown by this symbol. So you have a line and then two like filled circles, which is intended to reflect this inhibition. And as I already said, words are activated by the phonemes, but words can also activate phonemes top-down. Okay, so these models, they work in cycles when they're implemented in a computer. So you go through the network step by step, and each step you recalculate all values again. Let's go through an example, the recognition of the word cat, and each step we do could be a cycle in the model. So our auditory features in the beginning just tell us, okay, we heard the phoneme C. So on the phoneme level, what we have is that the first position of the first phoneme is identified as C. And on the word level, like in the cohort theory, we activate a number of words by that, like can, cat, cop, and many more. Now, when we have activation on this word level, we said we have feedback information, top-down influence, on the phoneme level. So what happens is the word cat, when this has some activation, it feeds back to activate the C as the first phoneme, but also already gives some activation that the second position may be at A and the third one at T. Can also activates the C, second phoneme as A and N. So these words then result already in some pre-activation of the phonemes, which can explain, for instance, some priming effects. Then we hear the next phoneme, the A of cat. Now, what happens now is that as a second position here, the A is identified. That's the phoneme, which actually is true. It's already pre-activated, but it's not the O. So our activation of cop disappears. And because this activation disappears, this pre-activation disappears also. So the P doesn't receive any more pre-activity. And as I said, all of these steps are cycled through when you actually simulate that model. You calculate that one after the other. Then you hear the T, and the same thing happens. You see third serial position actually is a T. Lateral inhibition takes place. Can is removed from the potential words, and so all the top-down influences of can also are removed. And this then, if you realize the word ended here, then you see there are no further options, and you finally identify and recognize cat as the word that you heard. And in this principle, these connectionless models work. Yeah.
How do you realize the words ended? Did you say last week's
Yeah, I don't know whether trace has a model for them. In trace, probably, there's just not more input. You know, it's just finished. In real life, that, of course, poses a new problem. You could, for instance, have, I don't know the real answer to that because I'm not a specialist in that area, but you could imagine that you have constantly multiple processes running. So which say cat, and then when new input comes, you simultaneously try to identify a new word and prolong the old word. And then you will see what makes more sense. Do you get a new word starting from that position, or so if TLE follow, you will get cattle in the end. So you work on with that one, potentially, or you may find a new word, actually. So that could be an extension to that model, how it works. But in word separation, you have quite strong top-down influences as well about the context, so that the context may make with the word cat much more likely than cattle, for instance. Like I was home and had my cat on my lap, so hopefully not your cattle. Okay. So this model has some strength. Because it's a computer model, it's very well specified. So that makes it possible to actually simulate real data. So they say, how do participants behave, and can I predict that? And you can make new predictions and test that on participants, for instance. It nicely explains how top-down and bottom-up processes can interact and explain these context effects. And because of all that, it can explain a number of empirical findings, like the categorical speech perception, where we only hear a da or a ta, even if we morph between the two. Then the categorical perception is explained by this winner-takes-all principle. On one level, you have represented only da or ta and other phonemes, and one is winning. You can't have the situation where, for instance, both win and you perceive a mixture of both. That can't happen in that model. It can also explain the so-called word superiority effect. And that's a finding, first reported by Ann Cutler, where your task is to detect a specific target phoneme. So you listen to input, auditory input, and for instance, I may tell you, okay, press always a button when you hear an L, something like that. Now, to show the word superiority effect, you have two conditions. In the first condition, the target phoneme, like an L, occurs in a sequence of phonemes which form a real word, like laughter. And then you have a second condition where it occurs in a non-word, which makes sense. So maybe laughter or something. I hope that's not an English word. And what you can show empirically is that in this condition you are faster than in this condition, although your task is only to identify a phoneme. However, that the phoneme is part of a real word makes the task easier. We will see later there's exactly the same thing when you do the task visually, in visually presented words. And the explanation by trace is that only real words can be activated bottom up by the phonemes and can spread back activation to the phoneme level. You don't have these additional activation of top-down influence by non-words because they're not part of your lexicon. They won't be activated. And response times are often described here or explained by level of activation. As soon as, for instance, the representation of your target phoneme L exceeds a threshold, you know it has been there, you press a button. So this additional activation from top-down word level helps you identifying the phoneme. Of course, it has some weaknesses again. So the vocabulary is limited to one-syllable words, as I already said. And the point is, and I think the question we just had points into the right direction already, it is unclear whether it would easily generalize to larger lexicons and longer words. Even two-syllable words may be a problem for this model. There is no learning implemented into the model. That means the lexicon and all the connections between the layers are set up by the experimenter at the beginning. And so you can tweak it if you want to your desire, and as long so that you get the desired output. And in the original form of the model, the top-down effects are sometimes overemphasized. They are actually smaller than predicted by the model. So, okay, to summarize, we started with a theory of speech recognition with the motor theory, which said that the speech recognition happens by covertly performing the motor acts in our motor system, as if we would produce what we heard. Then we have seen the cohort theory, so while this is very general about speech recognition, this is about word recognition, basically, the cohort theory. And the idea is that we get or identify finally the word by starting with an initial cohort of all potential words and narrowing that down until we have our final winner. And the trace model, finally, is a connectionist computer simulation, which nicely incorporates these bottom-up and top-down influences into a single model. Okay, do you have any questions on these theories of speech recognition? Okay, so then let's go to visual word recognition. So what we spoke about so far was the auditory input of speech. Now it's about the visual process of language. And one of the things in visual word recognition people are interested in is, for instance, the reading speed. So typical college students read around 200 to 230 words per minute. Excellent readers, student readers, up to 600 words per minute. And then you probably have heard of these speed reading trainings, that you can increase your reading speed incredibly. And one of the techniques for doing that is called skimming. And skimming is basically that you screen the text for important information before reading that in a bit more detail. So in these speed reading trainings, there's always the trade-off between speed and accuracy, or in this context, text comprehension. So of course you can read incredibly fast, but you didn't take up any information. So in all these reading speed contests, the contestants are asked for comprehension, so they have to answer questions afterwards. And only if they are above a certain level, it is acknowledged that they actually read in that speed. So usually there's a trade-off that the faster you read, the less you comprehend the text. And usually at these reading contests, if you have top contestants, they read around 1,000 to 2,000 words per minute with around 50% comprehension. And the world champion, Anne Jones, reads around 4,700 words per minute with 67% comprehension. And to give you an idea of the speed, she read the latest Harry Potter and the Deathly Hallows in 47 minutes. So I think it has, how many pages? 600, 700 pages or something? So she's British, and I think she lives in London. It was like when the book was published, the media surrounded her. She read it, I think at Barnes & Noble or some bookshop, and so she was the first to give an opinion about the book and could report about the contents of the book. So, okay, so just to give you some introduction to that topic, and word recognition, as you have seen on the initial slide, is automatic. You can't look at a word and decide to not read it. That's not possible. You automatically will have read it, unless you close your eyes or something. And we've spoken about the Stroop effect already, so let's go through that a little bit more, or once more as a refresher. The Stroop task is basically used as a task to demonstrate that word reading, or as one of its purposes, or it's used for sometimes, to argue that word reading is automatic. So we had this task. The original Stroop task is either naming color plates like green, blue, red, and the other one is name the color of the ink of the word, so green, blue, red in this example as well. And what you see is that when it is inconsistent here, so in this example you have to say green, but the word says red, you are slower, so you experience Stroop interference. And we did the demonstration last time, so we won't go through that in too much detail, but for the people who haven't been here, I will try to do my best here now in the front, so I will make a fool out of myself, and just read it, and you probably already can see this difference in speed. So naming the colors of the words here is quite easy because it's compatible. So it's red, yellow, green, blue, red, blue, yellow, green, blue, red. So that's easy. Now the difficult one, the incompatible, is yellow, green, blue, red, green, yellow, blue, red, green, yellow. Okay, so I actually did my best. So it's not like pretending for purposes here. It's really difficult, you know that from the demonstration. And then we can skip that. You can have a control list where you don't have any words associated with that. Okay, so, and there are different explanations for that. And one is the automaticity hypothesis. And this states that reading is automatic. And because it is automatic, if you remember back our lecture on attention and the distinction Schneider and Schifrin made on automatic processing and controlled processing, automatic processing cannot be controlled. So we can't suppress the reading of the color word. So when color word and the ink are incompatible, we always suffer interference because we have two color informations in our mind. And support for that theory comes from when you do take participants who know two languages and have a second language, and you do that in the Stroop task with the second language, you get less Stroop interference. Usually because there's not such a strong association. You don't read so automatically in the different language. An alternative hypothesis is that it's actually about the speed of processing. Because reading is so highly trained, we are much faster in reading the word than naming the color of the ink in the word is written, because that's much less. And there are experiments which try, for instance, to recreate the Stroop task by something which is neutral in the beginning, by two tasks like this, reading and color naming. Reading is highly trained, color naming not. You can do Stroop tasks in all varieties, and you can pick two tasks which are equally well trained. And then you train one of them very strongly, and then you suddenly experience Stroop, and then you try to revert that by, for instance, training the other task and stop training and things like that. So the idea of speed of processing is that you have a race of information, the race coming from the word and the race coming from the ink color. And word information just is faster because it's so highly trained. So if we have a decisional stage to say what is the color, what's the true answer, the right answer, then the information which comes from reading just wins this race. Therefore we have interference. Support for that comes that if you take the reading speed of people, slow readers have less Stroop interference. And that's what I meant before. This automaticity of word reading aids letter identification. So we have a word superiority effect also in the visual domain. Suppose the following task. First condition is where you have a single letter. So participants first on this see a blank screen, then they see a letter to identify. However, this is presented only very briefly and is masked afterwards. So it's somewhat hard to identify. Otherwise, the task would be too trivial. And then you have to make a decision. The letter you have seen, to choice, was it either the left one, D, in this example, or the right one, G, in this example. And then you take performance. In the word condition, you basically have the same condition, but now the letter is embedded into a meaningful word. And what you find is that this condition, you're faster. Although people could argue if it's really only lower level and letter detection, this task actually should be harder because your target letter, which is just identified by being underlined, is harder to detect among the distracting other letters. But actually, that it is a word helps you here in detection. Okay, there's quite a bit of research which investigates the process of reading. So when people really look at a text, what are they doing actually? And one of the methods is eye tracking. So you have nowadays a lot of different systems. This is one where you actually have to wear the camera on top of your head in a kind of helmet, and then you have two little cameras here which directly look at your eyes, your pupils, and then can see where exactly are you gazing. You have additional sensors here on the screen to see the position of your head, so to account for that, so that people really know where are the participants are looking at. This is a different system where you don't have to wear a helmet or anything, which is just attached to the computer, and therefore it's a little bit more convenient. These systems work differently to what has become popular in mobile phones recently a little bit, where, for instance, if you look at the bottom half on your mobile phone, the text scrolls up automatically. You can set that in some phones. This is on a much coarser level. Here you can really very exactly, with a high time resolution, a high spatial resolution, identify that. On mobile phones it's more about bottom or top of the screen or something. And you may know and have heard about that when we do eye movements, they're usually not smooth, but done in saccades. So we jump around with our eyes. And usually we get input or process the input only during the fixations, which are between saccades. But during the jump, during the saccade, we don't take up information. So in reading, the fixations take around 200 to 250 milliseconds for good readers, and in children or slower readers they take longer. So that's one reason why you read slower, you just look longer at the words. In addition, difficulty of the text affects the duration of the fixation, and as I said, information is only gathered during that time. So using an eye tracker, you can actually draw like these schematic things where you can see where people looked at if you have a sentence. So you start here, you go here, that's a fixation, next fixation, next fixation. These are always saccades. Then you go jump to the next line, do like that. And what we have here is called a regression. So you jump from here to here, and the jump may have been too big. You jumped 2 words, and maybe, or 3 words actually, and no, sorry, 2 words, and you may have missed some information, maybe you can't understand it properly, so you jump back, and then you go forward in smaller jumps. So this happens as well. It's of course not always conscious to us what we do, because reading is so automatic, we just do that. Same thing is often done in like perception of visual faces, other visual stimuli. You may know these things. When we see a face, where do we look? It's mainly the eyes, and then nose, mouth area, which is mostly looked at by participants. So that's the same thing here, which is used for reading. One of the things people investigate, for instance, with eye trackers, is something which is called the perceptual span. And that is our effective field of view in reading. So when we look at one particular point in the text, how much information do we take up to the left and to the right from that point of fixation? And first of all, you may know that we see sharp or in focus only in the fovea. Everything else becomes blurred. And our perceptual span, which we use for reading, is larger than the foveal vision. That means we take into account also blurred information. And this information, which has a rather low acuity, is, for instance, used to identify word boundaries, to determine where the next saccade should go to. And the perceptual span, then, if you want to express it in centimeters or something, then of course it's affected by the size of print, the difficulty of the text, expertise of the reader, and so forth. So fast readers may have, or good, well trained, may have a larger perceptual span and may do larger saccades actually. And the usual average perceptual span, let's say, is that you only go 3 or 4 letters to the left and around 15 letters to the right. So it's not symmetrical. When you focus, it's a little bit to the left, which is natural because to the left is what you have read, what you just read. So you're not interested in that anymore, and there's much more intake from the right. This is depending on your reading training. In Hebrew, where you read from right to left, it's exactly opposite. Then you have a short span to the right, and the large span goes to the left. So it has nothing to do with like hemispheric differences or so. It's really just reading training. And then you can do funny experiments, which can be sometimes weird for the participants. And you can use different techniques using the eye tracker. One is the moving window technique, where this is the point where the participant looks at, the fixation, and where you block out other parts of the text. And when the person makes a saccade, during the saccade, where the person doesn't realize anything anyway, doesn't perceive anything, you move this window. And by varying the size of the window, you can see how do the saccades change, how does the text comprehension and reading pattern changes. So by this moving window technique, you can, for instance, find out the perceptual span. And I can tell you that if you do that as a participant, that can feel very weird, because we are not used to the fact that our eyes actually have an effect on our surroundings. We are used that we can affect things with our hands, so actions have an effect. But our eyes usually don't. And already the calibration of that thing, where you sit in front of the screen and you have to look at dots, and as long as you have fixated long enough, the dot disappears and you look at the next dot, like calibration of the touch screen or something. It feels a little bit like you press a button with your eyes, and already that is a little bit a strange feeling because we're really not used to that. Okay, that's all what I just said. Another technique is the so-called boundary technique, and what we do here is that when the saccade happens, what we do is, during that time where there's no perception, we change some of the text. So the person reads initially several theories of structure have been developed. So when focusing here and then theories of structure jumping here, when he lands here, suddenly there's the word expertise. And this again tells you something about, do people notice that or not? How does it affect reading pattern? How far in advance, how much information is picked up? And how far does that go? Another example is here, given that somewhere in advance the word developed has been replaced by some arbitrary letters here, and when you jump there, you bring it back to developed. So there are different ways to do that thing. And again, you can trick the participant here. Okay. There are differences in the word categories in how much attention do we pay to them. So one aspect of whether we look at a word during reading or not is the functionality. The content words are virtually always fixated, so about 80%. However, only 20% of the function words, like the articles, are actually fixated during reading. So, and you may notice that your saccades, they don't go from every word to every word. That would be very slow reading. The frequency of words, and frequency means how they occur in natural language. So we have rare words and we have very common words. And you can see that rare words are fixated longer than common words, which goes a little bit along with this automaticity explanation, because rare words are less automatic than very common frequent words. The predictability, so if a word is very predictable from the context, then we look at it for a shorter time. Also, when we have short words, they are looked at a shorter time because it's faster to identify them. Okay. Do you have any questions on visual word recognition? Okay, then let's have a little bit of break before we go into syntax processing. Okay, let's go on. And I hope you had a little bit of a refreshment now, because it gets a little bit complicated now. It's about the processing of syntax and how we do that. That means the grammatical structure of sentences. And once more, we have to refer to Noam Chomsky, because the basic concepts which are still used today go back to his theories. So the question we start with is, how is it actually possible that as humans we can produce like an infinite number of new acceptable sentences? And why don't we virtually never produce unacceptable sentences? So how can we use language so well? And Chomsky suggested that we use a set of rules to generate the sentences. And he called that the phrase structure grammar. There are other grammars, but we will focus on this one. So this means we have a grammar, a set of rules, which determines how we structure the phrases of sentences. And this phrase structure grammar is often represented as an inverted tree. We'll see an example in a moment. Okay, let's start with a very simplified grammar to just illustrate that. So we may have a sentence such as "the boy read a book." And we may have this note that, okay, there is a sentence. And our first rule may be that a sentence consists of a noun phrase and a verb phrase. So with a noun phrase abbreviated as NP and a verb phrase abbreviated as VP. Our second rule may be that a noun phrase consists of an article, which sometimes can be omitted, and a noun. So our noun phrase consists of an article, the, and a noun, boy. So the boy is our noun phrase in our sentence. Now we still have the verb phrase, and the verb phrase can be a verb plus a noun phrase again. But this can be omitted as well. So the verb phrase may be just a verb. The boy read may be a proper sentence. However, we may have in addition another noun phrase like here, which consists of an article and a noun. So this is this inverted tree, so to say. You start with a stem and then it branches out until you are here at, so to say, the top of the tree, which is then describes the structure. Then there are rules about which words can be used for the grammatical categories. The article is the and a, the noun is boy and book in this example, or other nouns, and the verb can be read, was in this example, or further verbs. These three rules are, of course, a very simplified grammar, but it nicely illustrates how that works. Our real life grammar has just much more of these rules, so it's more complex. But the underlying principle and idea stays the same. Okay, so, and the idea is, if I, as the speaker, would like to generate a sentence, in my mind, so to say, I start at the level of S of the sentence. Then I unpack that sentence into noun phrase and verb phrase. Then I unpack these two and so forth. So that I finally come up, okay, I want to express that idea, and to do so, I have to use that sentence, that grammatical structure. Yeah, and as I said, the real grammar, of course, is more complex. Okay, now that was the perspective of the speaker. Now, as the listener, we have the same kind of, or no, it's even more difficult for us. Because when we hear or read a sentence, we have to infer on that tree. When we construct it, we just need to adhere to the rules and we have it. However, as we will see, there are many examples where we have a choice between multiple trees, so where it's ambiguous. So as a listener, it's a quite complex task. So how do we generate such a tree as a listener? And that question is referred to with the word parsing. So we have to parse the sentence to properly understand that. And yeah. So yeah, we have to come up with such a tree, otherwise we don't understand it. Now, how can we deal with the ambiguities which are there? And this is an example. There are two different ways of reading that sentence to assign that. One is, they are boring students, so the students are boring. Or they, these people, are actively doing something which is boring the students. So, yeah, so the students are bored by them. How do the trees look like for these different readings? So, in this example, these students are boring. So, it's a characteristic of the students. Then we have they is the noun phrase, the students. And then we have the verb phrase with the verb are, the students are. And then we have, as we have seen, another noun phrase, which is in this case an adjective. That means a describing property of the noun. So they are boring students. The other reading results in a different tree. So here again we have the noun phrase they, but then we have a verb phrase here which has an auxiliary verb and the main verb are boring, and then we have the noun of the verb phrase students. So this example illustrates there are ambiguities, and both readings can be reflected by different trees. Now there are examples where you have the situation that many people read it in the same way when there are ambiguities. And the question is, how can we see or describe this common or most prototypical or typical interpretation or building up of trees? And this has been suggested in a theory proposed by Fraser and Rayner, and they explain that in what is called their garden path model. And the name comes from the fact that it explains some phenomena where people are misled in reading sentences, or in other words, led up the garden path. We will have an example in a minute. Okay. And they suggest that this tree during parsing is constructed like bottom up while we hear and or read the sentence. So hearing beginning don't we have a picture here or something? No. I don't know where the boy now comes from or refers to. Okay, so it starts when we start hearing the sentence. We immediately start to construct a tree. So we don't wait until we heard the whole sentence and then try to process it, but we start immediately. So we start creating partial trees. For instance, where there's just an S, a sentence, and a noun phrase. Although we don't know, we just have the boy. We just heard the boy so far. So we know it's probably a sentence and we have a noun phrase. And one of their arguments is, or one of their propositions is, that we always construct only one tree or partial tree at a time. So when there are ambiguities, we don't create all possible trees, we decide for one tree. And only if we later find out that tree doesn't work, we try another one. The advantage of that is that it minimizes the load on working memory. Because reading, or this is affecting text comprehension, getting the grammatical structure is quite challenging. So creating all possible trees would be much too challenging for our working memory, where you know that it's quite limited. Okay, so which trees are constructed when there are choices? And they proposed some rules for that. And they said generally, we try to use the simplest syntactic structure which is possible to read that properly. And this is expressed by two rules or assumptions. One is called minimal attachment, and the other one is called late closure. And we will speak about these in detail with an example. Okay, let's see an example for minimal attachment. And that means that preference is given, or we choose the tree which has the smallest number of nodes. Nodes are these things: sentence, verb phrase, article, noun, things like that. Consider that sentence. It's a syntactically correct, proper English sentence. Most people struggle in the first reading. Quite a few get it after some time. Some struggle always. The reading is, the horse which raced past the barn fell. So that is the correct reading of that. Now let's look at how we construct our tree according to the garden path model. So initially we want to do that when we read that, and that's an expression of minimal attachment. We first hear or read the word the, so we are in a noun phrase. So we are now kind of fishing for the noun. We have the article, and then we read horse. Okay, we have our noun. When we have a noun phrase, we know we are in a sentence. And we know when we are in a sentence, we don't have only a noun phrase, we also have a verb phrase. So we need a verb. We are fishing for a verb. And now we read raised. That makes perfect sense. The horse raised. So we take that as the verb of the sentence. Past the barn which is called a prepositional phrase. And it works as an adjective or adverb. That means it just qualifies where did the horse race in this example. The horse raced past the barn. Perfectly valid sentence. And then the weird fell comes in the end. Now our parser is lost. Where should we attach that to our tree? There is no point where another verb could be attached here. So we have a problem. In our original reading, we have 5 nodes. 1, 2, 3, 4, 5. So that's proposed or suggested by the garden path model that we read it like that. Now, after some time, our parser realizes that the actual sentence is the horse fell. So this is of our sentence the noun phrase and the verb phrase, and this is something in between. So we have to modify our path, our tree. So the verb is actually fell. So this is our verb phrase, and this in the middle is which is called a reduced relative clause. So it's basically another sentence which is kind of reduced. So we have again a sentence structure of a verb and a prepositional phrase. Because it's a relative clause, it can miss the noun phrase. And this relative clause is attached to this noun phrase because it refers to the horse. So this is the correct reading of the sentence, where we say noun phrase and then do it like that. In this reading, we have 7 nodes. 1, 2, 3, 4, 5, 6, 7. So it's more complex. It has more nodes. So it's not the reading which is initially chosen by our parser. And if you go into linguistics and the study of that, you will see so complicated trees. So people really try to describe everything with these trees, and you can go crazy with that. Okay, so yeah, that's what I said. Minimal attachment predicts the initial reading. It's noteworthy that the whole effect hinges only on the ambiguity of the word raised, because it can actually have 2 meanings or belong to 2 categories. It can be the past tense verb, so the horse raced yesterday, or it can be what is called a passive participle. That means a word describing a noun, the raced horse, as it is used here. And we naturally, as we have seen when we construct the tree, prefer that one. If there is no ambiguity, there is no difficulty in reading that sentence. So it's the same grammatical structure. The car driven past the barn crashed. We immediately get the correct reading, because driven can only be the passive participle, but it can't be the past tense, because that would be the car drove past the barn. There are quite a few examples where you can create that ambiguity. So for instance, this sentence, the old man, the boat. And most people struggle initially because you read the old man, or the man who is old, the old man, but it actually means the old people man the boat. So there are some more examples of that. Okay. So we said when we have ambiguity, we take the simplest syntactic structure, and we have seen the rule or the assumption of minimal attachment, how that affects the reading or understanding of syntactical processing. The second rule was late closure. Let's have a look at that. So the idea of late closure is that our parser always tries to attach new words to our current phrase. It doesn't want to start a new partial tree or something like that. So we get, this minimizes the number of phrases and complexity in our tree, and therefore it kind of ensures parsimonious trees. So think of the following example. Most people struggle here. Most people read because he always jogs a mile, and then they struggle. Seems? That's weird. Then you go back, and then you reread because he always jogs a mile. Oh, sorry. Because he always jogs, a mile seems like a short distance. So let's have a look what our parser wants to do. So initially, because he noun always jogs, the verb. And then a mile is presented to us. And according to late closure, we just want to attach that to our sentence. We don't want to start a new phrase, we just attach that. And it makes sense here. So he jogs, and then we get further information because he always jogs a mile. That qualifies that. So he doesn't jog 2 miles or something. And then seems comes. And we can't attach that. It hangs in the air to that partial tree which we constructed here. So we have to reconsider to see, okay, we are not allowed to attach a mile to that part, but it actually is a subject to seems. So it's a more complex tree. In this example, the ambiguity can be easily removed by punctuation. So in that reading, because he always jogs, comma, a mile seems like a short distance to him. Then there's no ambiguity. And in verbal speech, everyday speech, we can use prosody for that. We can say, because he always jogs, a mile seems like a short distance. Then it's clear as well. So when we want to have the other reading, we have to slightly change the sentence. Because he always jogs a mile, then we do comma, and then we need an additional noun here. It seems like a short distance to him, because mile isn't the noun to seems anymore. And that's a slightly different sentence. Okay, so the garden path model is quite simple and straightforward and can explain a range of phenomena. But it turned out that some assumptions are actually incorrect. So what they suggested is that the parsing is purely based on syntax information. Information from meaning, from semantics, is only considered after parsing. However, it can be shown that meaning already affects parsing. So there are examples of this late closure which pose no difficulties to us because of the meanings. Read that, for instance. According to late closure to the model, we should think that that in a box is attached just here, so there is a boy in a box. However, most people don't read that. They will read that there is a gift in a box, and the gift was for the boy. So it's initially parsed correctly, and this can only be explained when we take semantics into account. Okay, to summarize, we have seen that the assumption or the construction of a phrase structure grammar is proposing a set of rules to create and understand sentences so that we can generate and understand them. So they are illustrated or represented by these inverted trees, and there are quite a few different variations or models or theories, you may say, which are based on that. And on a more larger level, this is one type of grammar. There are other types of grammar existent. Okay, do you have any questions regarding that? Okay, let's go. I think it's the last topic, and it's rather short for today. Text comprehension. So going one step further, the understanding of whole text, paragraphs, multiple sentences. So text comprehension is defined as the ability to read a text, to process it, and understand its meaning. So for you as a student, text comprehension is quite an important thing, because you have no effect or no benefit at all if you read a textbook and you don't understand it. If you just read the words and you know what the individual words mean, but if it doesn't make sense to you, then it's no point. So usually text comprehension is studied in reading, because it's just the easiest mode and a mode where we convey a lot of information. And it has been shown that there are many, many factors which affect text comprehension, and we will speak about only one of them briefly. So first of all, it's language skills. How good are you at phonology, syntax, semantics, pragmatics? If your skills in these areas are good, it's very likely that you're better at text comprehension. The argument is, if you lack these basic abilities, then you're slower, there may be more ambiguity here, so that the text comprehension is affected by that. So the ability to recognize words quickly and effortlessly. So word recognition. How trained are you? How easily can you access your lexicon? Of course, prior knowledge about the subject. So if you are proficient in an area, it's much easier to read a research paper as compared when you are new to that area. Generally, the ability to make inferences, because that's a lot what you have to do when you read a longer text and you have to comprehend them, get the logical arguments which are embedded in there in the text. Skills to monitor comprehension. So for instance, asking yourself a question, this bit of information I'm reading, is that really essential for my understanding of the text, or is it not essential? Can I rather disregard that? Why is it important? Where do I have to integrate that into my knowledge base? Things like that. So do I need to read that all or not? Things like that. And one thing, because it most closely links into our topic here, cognitive psychology, is also working memory and your abilities in working memory, which affect reading comprehension. So let's have a little bit closer look at that. And the role of working memory for reading comprehension was investigated, among others of course, by Justin Carpenter. And they had proposed a capacity theory of working memory. And they said that working memory is one thing, the short-term storage of information, and the processing of that information, as we spoke about already in the lecture on short-term memory. And the capacity of working memory is limited. So you only have a limited amount of capacity to store and to process information. However, it has also been proposed that the capacity varies between individuals. And there are tests like working memory span tasks which are used and which are shown to correlate highly, for instance, with general intelligence. So there seems to be some relationship and that the capacity really differs between people. And they introduced what is called the reading span task to assess the capacity. There are now many variations of that. For instance, the operation span task, which doesn't involve reading something but involves mathematical operations, like little things like 3 plus 5 multiplied with 2 equals that 15 or not. You have to decide yes, no. Okay, let's have a look at the reading span task, how it looks like. And this is generally an example of a working memory span task. And here, what you have to do is you have to read sentences, a couple of sentences for comprehension. So later on you may be asked about the contents of these sentences. However, you have a second task, and that is that you have to memorize the last word of each sentence. And later on, you know that in advance, you have to recall these last words in the order of presentation. So let's have an example, and you can do that actually. So look at the screen, read the sentences properly, don't skim or something. Imagine you will be asked content questions about these sentences. And also, remember all the last words in the order of presentation. So think about how to report the words. Okay, the answer was zoo, white, moon, funny. And when you do the whole span task, what you will do is you will do different length of trials. This is an example of 4 sentences, 4 words. And you can increase that 5, 6, 7, and that way you can determine your span, your working memory span. And what you actually have to do here is 2 things. You have to read the sentence for comprehension, at the same time you have to memorize all the words. And this is quite a demanding task and taxes both components of working memory. Now what has been shown is that the reading span task correlates really highly with text comprehension. So it's a good predictor of that. And therefore, Justin Carpenter concluded that working memory capacity is an important factor in reading comprehension. So, it has been shown that people who have a high reading span, that means a high working memory capacity, they actually make more use of semantic cues. So when content provides you help in understanding, and that they sometimes even do have 2 syntactical interpretations in parallel, like what we have with these parsing trees, that they can build up 2 trees in parallel. And then later on, when they see one tree doesn't work, they already have the correct tree. So, taken together, working memory capacity seems to be an important factor in whether people are good or not so good in text comprehension. Any questions on text comprehension, reading comprehension? Okay, that's it then for this week. Next week we will have 2 different topics, that means 2 chapters from the textbook, but the chapters will be shorter. It will be about expertise and problem solving. Okay, see you next week then.